kids, your organization, with lots of health, wealth, happiness, and certainly lots of success. Thank you very much. Have a very beautiful day. And I wish all of you a very, very happy new year, with respect of all the challenges. I'm sure we'll be able to manage it. Thank you.
Sir. Great, yes, sir. Great.
Thank you, sir.
Thank you very much.
Thank you. Thank you.
So, after the Dr. E.V. Swaminathan's speech, we will go for the next one, third one session. Dr. Chandrajit Pal is with us. He will continue the session immediately after within a 2 minute. Dr. Chandrajit Pal, sir, are you with us?
Yes, sir. Yes,
Yes,
Pankaj, sir.
Yes, sir. Yes, sir. Please continue, sir, session. No problem. Thank you, sir.
Okay, sure.
Right, sir.
Okay, so I'll just share my screen.
Yeah, you can share your screen. Yes, sir.
Okay.
Sir, make it full.
Yeah. Okay, so today, good afternoon, everyone. So today I am going to start a topic on reinforcement learning. Okay. So yesterday we discussed about convolution neural network. That's a part of the deep learning process. So that's an artificial neural network. And today also it's a part of machine learning. A little bit new, but I think most of you have heard about. So this is on reinforcement learning. Okay, so yeah, I hope it will be interesting. I'll try to explain in the form of a story. So what is basically reinforcement learning? So like there are things, basically supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. 4 things, I'm sorry, it's 4 things total, different types of learning. So what is supervised learning? Let me give a very brief. Supervised learning is about whatever we saw yesterday. Say this is one case of supervised learning where we have a labeled data set. Okay, that means if I am being given the job to distinguish between cow and an elephant, okay, so I need to train my neural net or the classifier, the algorithm, with a labeled data set. And labeled data set in the sense I have the complete data set of cow and I have the complete data set of elephant. Okay, say suppose I have 5,000 images of cow and 5,000 different images of elephant, and I need to train my neural net. So it's a labeled data set. I mean, whatever pictures I have that has been segregated and placed in the folder named as cow, 5,000 different types of cow, different maybe the same image with different angles or whatever. I mean, all the pictures of cow I need to keep in a folder which is labeled as cow, and all different type of images which I need to identify as elephant. Different 5,000 different types of images of elephant I need to keep it into the folder elephant. So that's a labeled data set. So that is called supervised learning problem, because I am supervising, I am guiding my neural net to behave, to predict whether it's a cow and an elephant. At first the neural net will make mistake, but then from then onwards it will not make mistake. The error, the loss will decrease as we continue to iterate in the learning steps. So that is called as supervised, because the data set is labeled. Now what is unsupervised? Where there is no label present in the data set. Okay, so examples are like, for example, clustering. Okay, so I need to understand the underlying behavior, the data structure, the pattern of the data sets, and based on that I'm going to segregate it in multiple clusters. For example, I have been given 3 different types of fruits, and if I suppose I don't know the name of the fruits, I went to a jungle and there I am getting 3 different type of fruits, and I don't know, I haven't ever seen the fruits before. Okay, but I need to, I have the stock of all the fruits piled up together, mixed up together, and I need to, I have been given 3 different cartoons, and I need to segregate. I need to segregate those 3 different fruits which have been mixed together. So how will I segregate? Okay, I don't know the names, but I've been told to segregate out the fruits, same type of fruits, segregate out the similar fruits, similar type of fruits. So what I'll do, I'll just try to see the underlying pattern. I just see the morphology of the fruit. Okay, so for example, apples have all the apples are of almost similar morphology, and they are different from mangoes. Okay, so whether it's a small apple, whether it's a big apple, does not matter. Okay, but that will definitely be different to that of a mango. Okay, whether it's a small size mango, big size mango, medium size mango, whoever be the person is, he can easily identify sorry, the difference between a mango and an apple, and I can easily segregate it, okay, by just looking at the morphology. It does not mean that I need to know the name of the fruit. Okay, so that is basically unsupervised learning. So that is, I'm clustering the data points, the data distribution from the mixture based on the morphology, based on the underlying data structure, the morphology, the pattern, the behavior, whatever you call, whatever jargon you call. Okay, so that is basically unsupervised. So now we know what is the difference between supervised and unsupervised. Now there is one more thing which is called like semi-supervised, like text classification, text prediction. Say one example I'm giving you, because it is not possible to have the entire dictionary, entire vocabulary at once. Okay, definitely there is, I mean, there will be some vocabulary, some dictionary from where you can predict and you can classify and you can recognize the text, but there will be certain words which may be falling outside the dictionary. So those will be unsupervised. Okay, and supervised will be the text which you already know, which is already present in the dictionary. So that is why text classification, natural language processing applications are generally called semi-supervised problems. Okay, so we know about unsupervised, supervised, and semi-supervised examples. And the final one is the reinforcement learning, which you cannot call as an unsupervised problem, not supervised problem, not semi-supervised problem. It's a completely separate approach. Okay, it's a completely separate approach. We call it as a reinforcement learning problem. So let's see what you mean by reinforcement learning. I'll just try to explain in story. So this is one example. Okay, so a very basic example which we almost face every day in day-to-day life. That is how we learn to ride a bicycle. Okay, how we learn to ride a bicycle, that is actually a reinforcement learning problem. So suppose my elder brother taught me how to ride a bicycle. So while teaching me how to ride a bicycle, definitely he did not tell me, okay, you lean left by 45 degree, sorry, you lean right by 30 degree, okay, and 30 degree from the center of gravity. Okay, you again go forward some 30 centimeter or 40 centimeter, again you lean left by 25 degree, lean right by 46 degree. In this way we did not, I mean, we were not taught to ride a bicycle. How we learned to ride a bicycle? We fell on the ground multiple times, 100 times we have fallen on the ground, and from that mistake we had learned how to ride a bicycle. Okay, you all try to recall your experience, whoever knows how to ride a bicycle, that how did you learn to ride a bicycle? Okay, nobody had taught you in such a manner that you lean left or go right, or uh, okay, try to maintain your balance with this measure of degrees, this phase angle, like that way. Otherwise, if you would have learned in that way, we would have called it as a supervised learning problem. Okay, if somebody would have taught
Just
you by
simply forward ಮಾಡಿದ್ದಾರೆ ಏನು ಬರ್ದಿಲ್ಲ ಹಂಗ ಆ ತರ ಬಂದ್ರೆ ನಾವು ಬರ್ದಿರೋ ಮೇಲೆ ನನಗೆ ಫಾರ್ವರ್ಡ್ ಮಾಡಿರೋ ಅರ್ಥ ಏನು
if you would have been taught to ride a bicycle in such a manner that go left, tilt left by 30 degree, tilt right again by 45 degree, then I would have called that as a supervised learning problem. Otherwise, this problem is a unsupervised. This is a reinforcement learning problem. It is not an unsupervised learning problem either. Okay, so how we learned? We first rode a bicycle, tried to ride a bicycle, fallen down. Then from the second time we tried that, okay, what mistake I have done in the first step? Why did I fell down? What mistake I had happened? Maybe I couldn't maintain the balance because I myself had tilted in such a degree from the center of gravity which compelled me to get, to fall down without maintaining the balance. So that's an internal understanding, that's an internal realization that this mistake I have done. So from the next time I will not repeat the same mistake, and so that I can maintain my balance and I will not fall down. Again, second time, maybe we had not repeated the same mistake, but we have done a separate mistake, and as a result we again fell down. Okay, so first time we had done a mistake, we learned from that mistake, we did not repeat that mistake. In the second step we did a separate mistake, and as a result we fell down. Third step we did another separate mistake which is not same as that of the first two, and we again fell down, and this continues to go on unless and until we come to a particular step where we did not repeat all the past mistakes and we are successful in maintaining the balance and ride the bicycle. That means, in other words, whatever mistake we have done in the previous steps, we learned from it and we did not repeat the mistakes. Whatever mistakes we did in the previous steps, we learned from it. If we got a feedback in the form of a punishment. So we did some action. We got a reward for that action. That reward is in the form of a positive reward or negative reward. Positive reward means definitely a reward. We call it as a reward, good reward. And negative reward means a punishment. So we fell down means we got a negative reward. And we did not fall down, which means a positive reward. That means we did not repeat the same mistake. So that means we learned to ride a bicycle through our experience. And that is reinforcement learning. So everyone have faced this problem, and we have internally gone through a reinforcement learning phenomena to learn how to ride a bicycle. So this is a very crucial example you will never forget. That's why I thought of illustrating this particular example, that riding a bicycle is an example of a reinforcement learning problem. Now, this one more example let me give you. This is a Go board. This is one of the oldest games, similar to that of chess. We don't know who invented it. There is a dilemma. There is a confusion as to who invented it, but it's a very intelligent game, which was, came through in Asian countries. They used to play in the Asian countries. And so this Go board, people thought there's such a mind-blowing game, such an intelligent game. So people thought that a computer, we cannot train a computer to play a Go board. But that thought became wrong. So nowadays we can train a machine, okay, to play a Go board with a human. Okay, so and the machine. There are a lot of examples when the machine won the game. Okay, you surpass the human level intelligence and they won the game. Just like the Deep Blue which computer you all already know, which played against Gary Kasparov and the own also Vishwanathan Anand, own the chess game. So that's also reinforcement learning approach where the machine has been trained to to learn to play the chess, and whatever the moves the machine will take is been guided through the reinforcement learning approach. So but in a given second it can think of 1,000 permutation and combinations, and it will choose the best possible move where it will reduce the probability of losing the game. Okay, so that is, so here the name is Go boards, and the name of the game is the AlphaGo, and machine versus human. Okay, so so in most of the cases machine won the game, human couldn't. Okay, that means we have been successful in training the machine with the reinforcement learning approach as to how to play successfully Go board, Go AlphaGo, the chess, and win the game. Okay, okay, so this slide contains a lot of equations, so don't get puzzled with this. After seeing these equations, I'll just walk through all the equations in the next few slides, and then you will feel the interest. You will no need to by heart the equations, which are with the basic engine of the reinforcement learning approach is standing on these 3 to 4 equations, you can say. Okay, so once I explain in the form of story and try to correlate how this equation is related to the stories, you will feel the interest. Okay, so let me give you another crucial example, that is how to effectively treat a patient. Okay, so I mean, think of the scenario. You went to a doctor, you have a fever or whatever disease you have, ailments you have, you went to a doctor to for some care, okay, to treat your disease. So the doctor, after monitoring your health, will have a set of action plan, a care plan or action plan, it is said. So the doctor has got a set of action plans which the doctor will apply on the patient, so that the patient gets cured. Okay, so the patient, the doctor at first is monitoring the health of the patient, and based on the health state condition, he has a set of action plan, and then he will apply those care plans or the action plans on the patient one by one, and he will also get the feedback as to if the patient is getting cured or not. One after the other, he will get the feedback. That means the doctor is following a policy, basically. Now there are 4 points as to how you effectively treat a patient. When you call, when does you say that the patient got treated effectively? The doctor has been successfully applying an effective treatment on the patient. Okay, so the first point is the primary goal is to effectively treat a patient while minimizing costs. That's very important point, that because you may treat a patient, you may treat a fever of a patient, normal fever, but if the cost is huge, if you take 50,000 rupees to cure a fever, then that treatment cannot be called as effectively giving an effective treatment to the patient. Okay, because it is not affordable. Okay, second is that a physician has a set of action plans that he may perform on the patient, and for each action that he will apply on the patient's health, it will impact the state of the patient, and the primary goal is to achieve a policy with good outcomes at minimal cost. Okay, so that means the doctor has to learn the policy, has to get to know the optimal policy, so that he can effectively treat a patient with good outcomes, that the patient should get cured at minimal cost. So there are 2 criteria, that is the patient, he has to effectively treat the patient so that the patient get cured. First point, that the patient should be cured, and the second point is the patient should be cured at minimal cost. So if these 2 criteria are successful, then you can say that the doctor has been successful in effectively treating the patient by learning the optimal policy. Okay, So this is one example of a reinforcement learning approach. And in the second phase, we will see that how the doctor has been successfully and effectively treating the patient. Okay. So the doctor, set of action plans he has, let's call it as a set. This is the problem setup. Let's call it at set A, where this is like A1, A2, A3 until dot 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 until AM, a set of action plans where he is applying medication, some procedure, he done the tests, do some analysis. These are all like action plans, one after the other. Okay, because it may happen that the doctor has taken an action which may lead to a bad outcome. Okay, so that means the doctor will get feedback in that form that he has applied a medication which did not treat the patient well, and what he will do is he will try to give another set of action. He will try to apply another second set of action plan so that the patient gets treated, and then after applying that action also he will get a feedback in the form of the state change of the patient's health. So that feedback to him, and if again he sees that his action plan has failed, that the patient's health is not improving, he will apply another set of action plans, and in this way it will continue. And but if his first action plan has been successful in getting the patient well, okay, then I mean we call it as I mean the doctor is has done the diagnosis and the analysis correctly, and he's a good doctor. That is, he has been successful in learning the optimal policy and has applied the action plan, which has led to a good outcome. Okay, that is, the health of the patient has improved. That is, he got a reward, positive reward. Okay, so there is a randomness in how a patient with state S will respond to a given action, because how the patient will react to a particular action plan is random. We don't know. Okay, and what is the reason behind that? So there is a randomness in how a patient with state S will respond to a given action. The reason that randomness is present is because there are some randomness in the disease itself. Okay, so suppose the health of the patient is being given by these parameters: temperature, blood pressure, lab tests. Lot of parameters are there, and there will be certain parameters which is tagged as unknown. We don't know all the parameters. There will be certain parameters which has been tagged as unknown. Okay, so since we cannot take into account, it is I mean it is our problem that we don't know what are all what all states constitutes the health of the patient. There will be certain unknown factors, as a result of which we could not find out the exact condition of the health, and that is creating the randomness, because there will be some unknown parameters, okay, which is not in our knowledge, and as a result, I mean the way the health of the patient responding to a given action is unknown, okay, is random due to this unknown parameter. Okay, so the reason the randomness is present, because there may be some randomness to the disease itself, but in addition, the state S, which is a vector of some parameters that characterizes the health of the patient, those parameters may not be sufficient to characterize every aspect of the health of the patient. Okay, as I mentioned here, there may be certain parameters, and certain parameters are unknown. Okay, that is not captured by S. So those missing aspects of the health manifest some randomness, because those missing characteristics are different from patient to patient. Okay, so that means it's like a biological verification, that there will be few parameters which constitute the health of the patient. Okay, so some parameters will be unknown, and those unknown parameters may vary from person to person, that is from patient to patient, and as a result, there is a randomness in as to how a patient will respond for a particular medication. Okay, so there will be certain randomness, and as a result, a doctor cannot be 100% correct in applying an action plan, in applying a correct treatment all the time. Okay, so the thing is, here there are certain variables which we need to keep in our mind. Okay, which means since we are going through the problem setup, that is there is an environment, okay, and the agent here, the doctor is the agent who is interacting with the environment. So the environment here, you can think of the patient, health of the patient, okay. Then I mean he's interacting with the patient, so the patient is the environment, you can think. Doctor is the agent, patient is the environment, and health of the patient is the state, current state. And the doctor is applying an action based on the state of the health of the patient. So there is a state S denoted by S. A is the action which the doctor is applying an action on the state of the health. Okay, and then there is a reward. So SAR. Okay, there is a reward. So before the reward, what will happen? Given a particular state of the health of the patient, which the doctor is monitoring, the doctor takes an action. After taking that action, there is a state change. That is, after applying a medication, in this way you can think that after applying the medication, there will be a state change. That is, the condition of the health of the patient will change. Maybe the fever with which he came, the temperature will come down or it will come up, go up. Okay, so there will be a change after applying the medication. Okay, that is a state change. So we call that state, given a state, there is an action applied by the agent, and as a result there is a state change. Okay, and this state change, with this state change there will be a reward. That is, for example, if the temperature, if the fever goes down, so there will be a positive reward, and if the temperature goes up even after applying the medication, then there will be a punishment. But whatever be the state change, if it is a reward, then the doctor again has a set of action plan which he can take. Okay, some low dose medicine he can give, so that slowly the fever gets down, because he could see the positive effect after applying the action A. And if after applying the first action, if the temperature or the fever of the patient goes up, so definitely there is a negative reward or a punishment. Then based on that, again the doctor will take again next set of action plan, so that this time the fever gets down. Okay, so whatever be the reward, whether it a positive reward or a negative reward, okay, the doctor again has to take another set of action, okay, to make the health of the patient goes to normalcy. Okay, so it comes like that: S state, action A, state change S prime, okay, R reward, and in this way it continues. SAR, SASR, SR. In this way it continues. Okay. So here, as you can see, that it is denoted by the probability, because we don't know how the patient's health will respond to a given medication or an action plan. Is a probability P. S is the current state of the health of the patient. A is the action which the doctor has applied, an action A, and as a result, there is a state change of the health of the person, which is denoted by S prime. Okay, definitely, if there is a medication when the doctor is applying on the health to a patient, there will be a state change. Okay, there is a health of the patient, which is denoted by the state. There will be a change in the state of the health. So that change is denoted by a probability. That what is the probability that there will be a state change which is good, or a state change whose probability is bad. Okay, so this is the thing. This is the state S, which constitutes of all these parameters, and there is a state of the state change S prime, which is again consists of this set of parameters. And so this is the story, the problem setup. Okay, and so here, like, say suppose there is a 70% probability that there is a state change which may be good, and 30% probability with the state change may be bad. Okay, and say what happened is there is a current state of the health of the patient, and after applying medication, the state change is such that the temperature from 100.5 has gone up 102.5, and the pressure, which was supposed to be going down, because normal pressure BP we know that is 120/80, that's the ideal one. So 165/95 was high, so instead of going down, it again gone up 185/97. Okay, so that means this state change, can we call it as a good or bad? Okay, so this state change is definitely a bad state change, because we thought the temperature will go down, but it has gone up, and this blood pressure we thought of it it should go down, but it has gone up. So this state change after applying the medication is a bad state change, and as a result the doctor will get a punishment. It's a negative reward. Okay, so here you can see this is the reward, whatever be it, there is the reward R, SAS prime, and this reward is a negative, should be a negative reward, because the state change is bad. We can see from here. Okay, so there is a randomness in how a patient with state S will respond to a given action. If state S prime, that is this state, is better than state S after taking action A, then the reward should be high. Okay, if state S prime is worse than state S, that is its previous state, after taking action A, then the reward should be low. Definitely, the reward should be low, means it should be a punishment. Reward takes into account the state of the health as well as the cost of action A. Okay, that means, as I told, that the cost should also be minimized, besides improving the health of the patient. So both the criteria, if it fulfills, we can say that the reward is positive. Okay, so RSAS prime is the reward, which reflects the immediate impact for the patient after taking action A and transition from state S to S prime. Okay, so most of the video games you will see is following the reinforcement learning approach, the robotic arm application, the video games. Okay, those are all following the reinforcement learning approaches. So here I would like to show the entire engine. Okay, so this is the complete engine of the reinforcement learning approach. Okay, so the variable, the parameters, or basically we say the environmental variables, can be denoted in this way, that state equal to the health of the patient is denoted by the state, and which the doctor is continuously monitoring once the patient has reached his chamber, and the care plan or the action plan. Okay, the state and the action, this action will be taken by the agent, and these actions are called the action plans or the care plans, which the doctor will take, and the reward is the immediate impact. Okay, so after given a particular state, taking an action, the doctor is taking an action, whether be it applying medication or doing a small operation or whatever be it, taking an action, and as a result the state of the health will change, and that state change, okay, will be reflected in the form of a reward. So the doctor learns through this experience, basically. Okay, so that's the reason why we generally tell that, okay, we generally ask that whether the doctor where you went is an experienced doctor or an old doctor or is aged doctor or not, because we assume that if the doctor is aged, he has learned, he has gone through lots of experience. Okay, and through his experience he has learned not to repeat his mistakes. Okay, so that means the doctor has passed through a lot of experience, use cases, and from there he learned, and the probability that he will not experiment with the health of the patient goes down. Okay, he will not try to experiment with the health of the patient. Okay, if he is an aged doctor, we pre-assume that he is very experienced, and there's a less chance that he will do some experiments with the health of the patient. Okay, because if he does some experiment, with the health of the patient, there may be chances, okay, it increases the likelihood that the patient health may deteriorate after applying the medication, because he is playing with the health of the patient. But if he is certain about the fact that, okay, if these are the use cases, then I will apply these are the this set of action plans, and definitely there will be a reward, and definitely the health of the patient will improve. If he is very sure about that, this confidence comes with experience, because it may happen that this particular use case he has faced 5 times before, and he had repeated, he has made mistakes 3 times, and the last 2 times he did not repeat that mistake. So there is a very high chance that he will also not repeat the same mistake now, and this confidence comes from the experience, as I told. Okay, so the doctor learns through his experience, and this complete process is that he has gone through a reinforcement learning approach. That is, he will try to reinforce those actions, okay, which had led to good outcomes, and will suppress those actions which had led to bad outcomes in the past. Okay, so the goal of the doctor is to develop a policy that defines the optimal action to take when presented with state S. So the goal of reinforcement learning is to learn this policy. Okay, so I'll repeat, the goal of the doctor is to develop a policy that defines the optimal action to take when presented with state S. So the goal of reinforcement learning is to learn this policy. So now let's learn about what is happening in this state machine. Okay, so this is the state of the health, ST minus 1. Okay, ST minus 1 is the given state of the health of the patient, ST minus 1 at time interval T minus 1, say. And once this state is present to the doctor, he will take an action which is given by AT minus 1. The doctor will take an action which is given by AT minus 1 at time T minus 1. So the patient came to the chamber of the doctor. His state is given by ST minus 1. Monitoring this state, the doctor will take an action which is given by AT minus 1. So after applying this action, the state of the health will change from ST minus 1 to ST. Okay, just try after the other. Okay, now when state change ST minus 1 to ST, that means the state change is good or bad will be related by a reward. So that reward is ST RT minus 1 reward. Okay, now after the reward, whether it's a positive reward or negative reward, the doctor again has to take another action. Okay, so the current state is now ST. So the doctor will take an action AT. There will be a state change after applying that action AT from ST to ST plus 1. Again, since there is a state change, there will be a reward, because whether the state change is good or bad, whether the health of the patient has improved or not, will be reflected by a reward, which is given again by RT, and this cycle continues. So this engine is completely about reinforcement learning. So the reinforcement learning is sitting on this engine. I repeat, the patient came to the doctor. His state of health is denoted by ST minus 1. Okay, at time T minus 1, his health is given by, the state of the health is given by ST minus 1. The doctor, upon seeing this particular state of the health, takes an action which is at time T minus 1, which is given by AT minus 1. After applying this action, there will be a state change, which is given by ST minus 1 to ST. Definitely, just think from your common sense that when a doctor is applying an action, even a medication, there will be a state change. And this state change, whether it's positive or negative, will be given by a reward, will be shown by a reward, which is RT minus 1. So once the doctor gets a reward, whether it is a positive or negative, he has to take another action So his next action will be AT minus 1, AT, because now the current state is ST. So he will take an action AT. Okay. After applying the action, again there will be a state change. That is, the current state is now ST. There will be a state change from ST to ST plus 1. When there is a state change, ST to ST plus 1, again there will be a reward, which is manifested by a reward, which is given by RT. And this goes on and so on. Okay, so the doctor learns from these rewards because he has applied the set of actions, and based on that action, there is a state change which is reflected by a reward. So he will always try to apply a particular action which has led to positive reward. Okay, and the doctor learns through this complete cycle, through this experience, complete cycle of state, action, reward, next state, again action, again state change, again reward, again action, state change, reward. In this way it continues. So this is all about reinforcement learning, and the doctor continues this state until and unless he has learned to learn an optimal policy. Okay, so that the next set of actions will lead to positive outcomes. Yeah, so any questions until now? Yeah, so participants, any questions until now?
Sir, in foreign the type of treatment is going on?
Hello, hello, I couldn't
In
hear that.
foreign countries.
Yeah, in foreign countries, yeah.
That type of medical treatment is going on, is practically?
Yeah. So, it's a very good question. See, the thing is, this is a medical assistant system. Okay, that is, you cannot replace a doctor. You cannot replace a doctor, but you can definitely assist him with this decision-making policy. In his decision-making policy, you can assist him. You can develop a, assistive system. Okay, through which will run this reinforcement learning algorithm in the back.
Any that is popular or known name of the packages available, sir? Something practically just like software
So
package.
software package, I'm not sure at present because because these are all open source. Those are all open source software packages. They are definitely there are available software packages, but present I'm not well aware of the names. You can give a search, but so this is quite common in outside, in abroad. It is quite common. Okay, people use this and they try to cross check it, actually, whether the doctor's decision and this reinforcement learning algorithm output, how close they are. So they try to cross check, and from there they do an average precision. Okay, so they try to see whether the doctor who has given the outcomes 10 times and the reinforcement learning output is also given 10 times. So if they see that out of 10 it is getting 8, almost 80%, they are similar, then they go with they try to rely more on the reinforcement learning approach. Okay, because they found that 80% times whatever the doctor has predicted is same as that of the algorithm output. So their reliability on the algorithm increases. Okay, in this way, slowly they are trying to fully automate this particular thing.
Suppose I want to do in medical field, means I want to expert in AI, DL and ML or something, any specialization needed, sir?
Yeah, because no, this particular algorithm is completely based on AI, right? Okay, so like these are intelligent systems, smart systems for smart healthcare. These are being used. Okay.
Oh, AI means she included ML and DL also.
Yes, absolutely. So
Okay.
AI,
Okay.
AI is the complete domain is AI. Within
Okay.
that, there is machine learning. Within machine learning is a subset of AI. Okay, and deep learning is a subset of machine learning. Okay, so if I draw, it's a good question. If I draw, so this is basically AI.
Okay.
This is machine learning. And within the machine learning, there is brain
Deep
inspired,
learning.
which is deep learning.
Suppose I want to, I am joining AI course means it is included MI and ML and DL also. Okay.
Yes.
Okay. Okay. Thank you.
Because there are a lot of things within AI. So fuzzy systems, soft computing, lot of things.
Okay. Okay. Okay, sir. Thank you, sir.
Oh,
Thank you very much.
okay, thanks. So any other participants? Any questions regarding this reinforcement engine? Any other questions?
Sir, some online data science or data
Mhm.
scientist, it may be in which university we will take it, sir, for online free.
Actually, see, there are now at present lot of online courses. Okay, so and everyone is trying to project in a different way. Okay, in a most subtitle way and easy way, lucrative way. So that depends. It depends. Okay, so you can take a lot of courses. Okay, as a reference, and you can enhance your knowledge. That is one thing. And most particularly, I suggest textbooks, which are most important. You have to go through
Which one,
textbooks.
sir?
That
Facebook.
textbooks. Yes,
Oh,
whatever field you are doing, trying to get the expertise, try to go through textbooks. Okay, tutorials are okay, online video lectures are okay, fine, but the main thing is we should not. There is no substitute to textbooks.
what spelling, sir?
Huh?
Facebook, yeah?
Yeah, books. We have to go through the
Oh,
books. That
oh,
cannot be
book.
substituted.
Oh, by book only it is very good.
Yes,
Familiarity will be there. Huh?
yes.
Okay, thank you, sir. Thank you.
Hmm. Okay, so in few books you will be getting this kind of symbols, to which will denote the optimal policy. Okay, now few I think so one book is there, Deep Learning, just by Geoffrey Hinton, Jan LeCun. Those people are godfathers. Okay, so you'll get machine learning ebooks. Try to find these authors' books. Geoffrey Hinton, Jan LeCun, and Yosha Benzio. Okay, so the three people got the Alan Turing Award in 2019. Okay, so try to go through the textbooks written by these three authors as well as his students. Okay. Anyway, so these are the symbols which denotes the optimal policies. Okay, that maximizes the average over time, and you should also account for the outcomes and the costs. And it should be myopic. I'll be explaining what is myopic and what is non-myopic. Okay, and so we'll typically weight impacts on the near term more highly than what happens in the long run. Okay, so immediate impact
Sir,
means myopic.
your
Yeah,
recommendation
please.
about AI, handbook or any author or any publish?
Yeah. Okay, what I'll do is after finishing this, I'll just pass on this information to
Okay, sir.
you.
Thank
Hmm? Sure. I'll mail you, or I'll in the common chat I'll send you the information. So from there you can see, and if any other doubts, I'll answer to that. Okay. So the thing is, we typically do not know the probability, as I told earlier. So the question is, how can we learn the optimal policy without having access to the underlying probability? So the solution, as I mentioned, is we can experience the world and try things, record outcomes, and adapt and adjust the policy, so that over time we reinforce the actions that led to good outcomes and discourage the actions that led to poor outcomes. And that is the reason why it is called reinforcement learning. That is, we try to emphasize give thirst or emphasize those actions that led to good outcomes. Good outcomes in the sense positive rewards. Okay. And discourage those set of actions that led to poor outcomes. So reinforcement learning is the formalization of this challenge. Okay. So if you understand this particular engine, you'll be getting to know the entire reinforcement learning problem. So what is actually happening given any problem which you try to solve through reinforcement learning will be following this engine, has to follow this engine. There is no other alternative. So whatever programs you'll be writing, whatever scripting you'll be designing, try to design the agents, the environment, the actions, the care plans, the rewards, everything has to follow this engine, whatever be the application, whatever be the use case. Okay, is based on the experience. Is taking the optimal. We learn this optimal policy based on the experience. So in few textbooks, we'll be getting this type of architecture, this type of action plans. In few textbooks, you'll be getting some other symbolic representation. So don't get confused. It's all are the same. Okay. So here I try to give an example of a doctor and a patient. There will be other health monitoring, examples like the machine health monitoring, stock market analysis and investing. Okay, very unpredicted. Those are. So machine health monitoring means, say for example, we did a project of one Indian Navy. So there you need to monitor the health of the ship. Okay, the remaining life of the health of the ship. That is, superficially, if you see the vessel, the steel with which it is made, you will not be able to find out the cracks, the fractures which has arisen internally. Okay. However, when your ship is is on a voyage and it is in the middle of the rough sea, so that time that crack, okay, will try to propagate more and more, and it will come superficially, and ultimately it will lead to a wreckage of the vessel, and it may sink. There are high chances that it may sink. Okay, but while it started its voyage, an expert also couldn't figure out that it had developed cracks internally, because he is seeing it superficially, and even with sound, if he is putting some dongle on it with the sound also, he couldn't identify that there had been some cracks which had came up internally. Okay, so you need to keep some sensor, and those sensor data, you need to put some sensors on the some critical points on the ship, and from those sensors you can get some data with which you can classify that yes, they are the health, classify regarding the health of the steel. That okay, if the sensor data is giving some patterns, so good steel, healthy steel where there is no cracks, it will give some pattern of output, and when there has been developed some cracks, so the sensor output will be definitely vary, right? So from the sensor data, you can identify, you can predict regarding the health of the steel. Okay, and based on that, it will take some action on the fly immediately. Okay, it may tell you to keep a shield on that particular point, so that in the rough sea, it reduces the chances of damage. Okay, so like those are few action plans the automated system can take. Okay, some actuations it may take on the fly so as to reduce the chances of the ship being broken down and get sink. Okay, so that is one example. Second is one more example is the stock market analysis, the investing, which are very much unpredictable. Okay, and reinforcement learning can help you to get a good return of your stocks and equities. Okay, and do some analysis on that. Okay, I'll just try to come down to that example and try to view that in the form of a table. That is called a Q table. How we try to optimize that problem, try to make the problem simpler is suppose the patient is diabetic. The patient has come to the doctor and he is diabetic, and the doctor has to take certain actions. That is, he has to apply some insulin and some bolus dose. That is also a medication to reduce down the diabetic level. Okay, glucose, previous day glucose level and the new glucose level, whatever be it, there will be some change, and the reward will be low or high based on the action. So the action plans are applying insulin and the bolus dose, etc., on the diabetic patient so that the sugar level remains in a normalcy. Okay, it will not be too low and it should not be too high. Just like BP, if the sugar level is too low, it is also a bad indication, and if the sugar level is very high, it is also a bad indication. So it can lead to a fatal condition. Okay, so how we basically set up the problem here. So whatever be the range, we try to discretize it. Okay, we try to discretize it. Say minimum is 90 or a minimum say is 30, is starting from 30. We try to discretize this. Minimum is 30 and maximum is say 250 or 260. We try to discretize this state. Okay, so this is a state of the health where the minimum glucose level and defined by a minimum glucose level and the maximum glucose level. So we discretize, we break it into ranges, the state of the health. Okay, so we try to discretize and set it into set of bins. Okay, so say 30 to 50, 50 to 115, 16 to 118, this way, 215 to 250 or 260. Say, break it into bins, and the action. So this is a state of the health, and based on the state of the health, the doctor will take an action. So the action we saw, the insulin, continuous supply of the insulin and the bolus dose. Okay, so the insulin and the bolus dose, those are also being discretized in the form of bins. So why we discretize it? To make the problem simpler, right? So basically the main focus of discretizing it is to form a table. It's called a Q table, where the left hand side denotes the state and the right hand and the rows denote the state and the columns denote the action. Okay, so here we had discretized the states starting from 30 to 50, 50 to 115. What we saw in the previous, we had this is a continuous range, and we had broken it up into discrete ranges. And similar for the action also, we had broken it up into some ranges. So the rows denote the state and the columns denote the action. So why we try to do in the form of a table, that given a particular state, what will be the effective set of action, we can find it out from the exact coordinate positions. Okay, so if it is seen that okay, the state is 117, and so for that, what will be the set of action? The set of action is say 45. I will take this particular action, say will be lying into this particular coordinate position. So given a state, what will be the optimal action will be given by this particular coordinate position. Okay, so here that what we want to achieve in reinforcement learning is to learn the Q function. This is called the Q function, Q state A. So it is defined by the two parameters Q S comma A. State S denotes the state, A denotes the action. Okay, and is the Q function or a Q table we call it, which is parameterized by these two arguments of state and action. That is, given a particular state, what will be the set of what will be the probable optimal action will be denoted by this particular entry in that table. So what we want to achieve in reinforcement learning is to learn the Q function. Okay, so the table values of the table will get updated every time. Okay, and unless and until the learning algorithm is trained, the values of the Q table will get updated every time through the iteration. It will be continuously, it will be getting updated. Okay, so it will come to, finally it will come to a state when the table will be, the values of the table, the entries of the table will be no more updated. Finally, we'll reach to a particular point, which will be called as a saturation point, when we can say that the learning algorithm has reached to a saturation point where you can stop the learning process, when the values of the table will be no more updated, when we will see that even after training, the values got saturated and the values, all the entries of the table are not getting updated. Okay, at that point, we can stop our learning algorithm and we can conclude that the reinforcement learning has been successful, and the training has converged and the values of the table are not getting updated anymore. Okay, so at that particular time, you can say that given a particular state, which set of action to be taken, we can reach that particular coordinate with ultimate success. Okay, so what we want to achieve in reinforcement learning is to learn the Q function so that we can choose the action A, which can maximize the Q function or the Q table. In other words, it can maximize the reward. Okay, and this is again, as I told, this is again sitting, on that particular engine, which shows that how to execute this particular table is initialize the Q table with some random values before starting the training, choose an action A, perform that action. After applying that action, definitely there will be a state change, and that will be reflected through an reward. Okay, so the reward will be positive or the negative, that we need to observe the reward, and based on the reward, the doctor will take another set of action and that will update the Q table. Okay, so in this way, after updating the Q table, again the doctor will take an action, perform that action, there will be a state change, and that will be manifested by a reward. Okay, that will update the Q table, and again the doctor will take an action. In this way, the process, the engine will continue. In other words, the training process follows this path, this process flow, this engine, whatever you call, in updating the table until the table gets saturated, where no more updation occurs, when we can conclude that the learning algorithm has been freezed. Okay, and you can start your inference. So the ultimate goal is to learn this Q table, okay, or the Q function, as you can tell, Q table or the Q function. Okay, so now we will see these equations one by one before concluding. So the Q new is given by SA. This is the Q old. That is the entry of the table is Q old. The entry of the table is old. After that, you need to update the Q table with the Q new value. Initially, it is Q old. After that, you will update it with Q new. Okay, so Q old plus is the learning rate, and this is the reward, and this is Q old. If the reward is positive, that is, it should be more than that of the Q old, then what will happen? You need to add a certain value with the learning rate to the Q old to form the Q new. That is, Q new is nothing but the updated value in that entry. The old value, after the iteration, you need to update this entry table value, and that updated value is called the Q new. And with what you will update based on this particular equation, based on this temporal difference, this particular equation. So definitely, if there is a reward, that value should be more than that of the original entry of the table, and this will be a positive term that will be multiplied by the learning rate, and that entire thing should be added to the original value. Okay. However, if this reward is less, just try to understand that if the reward is less, okay, if it is not more than q old, if it is less than q old, definitely there will be a negative value which is coming here. Say suppose this is -2 and this is -5, so ultimately it is -7. Okay, so alpha into -7 will also be a negative. So with q old, it will subtract something and q new value will decrement. Okay, and if this reward is positive, definitely if the reward big than that q of q old, okay, so this alpha into a positive value, so totally it will be of some positive value that will be added to q old, and so q new will be more than that. The magnitude of the q new will be more than that of the q old. So you need to update that particular entry of the table with a particular value whose magnitude is more than that of it was originally. Okay, so that has been explained here in text. Okay, so this is all it is. Achha, so now we will see moving to a non-myopic policy. So till now what we had learned is a myopic policy. That is, it takes into account the immediate reward. Okay, so what is non-myopic policy? It takes into account not only the immediate reward but also the subsequent in future rewards. Okay, that is, in other words, suppose in the form of an example, I'll tell you. Suppose I am having high fever. Okay, I am having high fever and I went to a doctor and I told the doctor that, okay, uh, I told the doctor that you treat me, need to treat my fever immediately. Okay, I need to get my fever temperature of my body goes down within 3 hours. You need to treat my fever within 3 hours. The doctor will say, yes, fine, I'll treat your fever within 3 hours, not an issue, but there'll be a negative impact in the long run. Okay, there'll be a side effect that you may have to bear with in the long run, and the side effect is maybe I may get asthma. Okay, I may get asthma, a little bit of asthma in after 2 to 3 years, and that will be a side effect of that steroid, of that medicine or the antibiotic that the doctor will give me now, so that my fever gets down within 3 hours. So that means it will be a social. I mean, the doctor should be responsible. It's a social responsibility for him to mention me also. That, okay, if I need to treat your fever within a very short span of time, in 2 to 3 hours, definitely I'll give you a medicine and your fever will go down, but it may impact your health in the long run. That is, subsequent reward is not good. So I'm only concerned about my immediate reward, immediate effect, and I'm not concerned about my subsequent actions. But there will be case to case basis, it depends. Suppose if I'm a patient and I am always concerned about my future also, then I may tell the doctor, okay, you give me some medication. I don't want my fever to get down within 3 hours. I may wait for another 2 days to get my fever. Slowly, it will be a betterment. It will be an improvement. I may accept that. But in the long run, it should not happen that I may get asthma. The doctor try to give a medication where my fever will get down, not immediately within 2 to 3 hours. It may take 1 or 2 days, but my health may not be deteriorated or affected with asthma in the long run after 2 to 3 years. So that is actually a non-myopic policy. Whatever I talked in the previous example was a myopic policy. That is I was concerned about the immediate effect, immediate reward. I was not concerned about my long-term effect. So that's a myopic policy. But as a doctor, he should always follow the non-myopic policy, because he should not give some medication which may lead to an immediate reward may be good, but in the long run that medicine should not have an adverse effect on the health of the patient. Okay, so that is actually a non-myopic policy. So the doctor should follow, or the agent should definitely follow a non-myopic policy and not a myopic policy. Try to remember this. Okay, that is now we are switching from myopic policy to non-myopic policy, and the doctor should always follow non-myopic policy. So what were the problems? Myopic policy, that is, assume the state of the patient age corresponds to severe poor health, only learns to predict the immediate reward of the patient, does not take into account the long-term consequences, as I told. Okay, these are the existing problems with the myopic policy, and as a result, we should always be switching towards non-myopic policy, where the doctor should give some medication to the patient where he may not be getting the immediate impact in a very good way. He may take some time, 1 or 2 days, to get his fever down. Okay, but that is still good in respect to the previous one, where after 3 years the person was getting asthmatic. That should not happen. Okay, so that equation is governed by this particular term, where there is an extension to the previous equation. The previous equation was, this was q nu q old plus alpha is the learning rate. This was the immediate reward, the q old value, as we explained. It was a myopic policy, and moving to a non-myopic one, the equation changed to this as q new q old plus alpha. This was same reward plus one additional factor, that is the gamma, the discount factor. We try to maximize the subsequent rewards. This q old was same, just tried to extend it, this particular reward factor. We just extended by adding an additional term here. So now you see you are getting, I'm sure you are getting interest, and you will not need to by heart these equations to apply while coding. Okay, you need to, I mean, you can just try to understand the physical realization, and from there you can write down these equations by through your understanding. If that concept is clear from the story, then you can immediately write down from the myopic to the non-myopic. You can jump from the myopic to the non-myopic. That is, in the myopic, we told that the doctor was only concerned about the immediate reward. The patient, in other words, is concerned about his immediate bodily effect, the immediate reward. But in the non-myopic one, he is not concerned about not only his immediate, but also in the subsequent future reward. That is, he wants to maximize the q old value, these future rewards. You want to maximize it, and how much is given by a gamma factor. One interesting point to note here is, so this reward has been broken down into 2 points. Now this gamma factor, that is, this gamma is the discount factor which lies between 0 and 1. Suppose if a patient says, that is basically this myopic equation is being is an expansion, has been taken out from the non-myopic only. Okay, this is the parent equation, you can say. This is the parent equation from which we have derived the myopic one. How? From this equation, just see if the gamma is 0. Just put this gamma is 0. This becomes same as that of this equation. There is alpha reward minus q volt. This term becomes entirely 0 if I put gamma is 0. So this discount factor, what is this discount factor? This depends on person to person. Suppose I came and I told, yes, within 2 hours I need my fever to get down. I'm least bothered about my health, what will happen after 2 to 3 years. So my gamma will be extremely small value, very close to 0 or even 0 you can put. So if this is 0, then this equation burns down to myopic one, because this term becomes completely 0. However, if I'm a follower of non-myopic policy, then I'll be asking for a gamma value close to 1. So in that case, this equation will return back. Okay, so it depends. This gamma factor depends on person to person, whether I'm a follower of a myopic, which is the previous equation. In that case, I'll ask for the gamma value to be 0. And if I'm a follower of a non-myopic policy, then definitely I'll try to choose the gamma value close to 1. Okay, in that case, this equation will be written back. That is, I'm not only concerned about my immediate reward, but I am also concerned about my futuristic rewards, which is given by the maximized value of the Q world. Okay, so this is an extension of myopic to a non-myopic one. Okay, so in some textbooks you will also see it's written, it's just rewritten. It's called a Q learning, is rewritten in this form. The things are same. It is Q nu equal to Q old plus alpha reward plus gamma of this minus Q old. So this is a non-myopic equation. From here you take 1 minus alpha, this is a common with the Q old. Okay, so this alpha R, complete thing is present within this bracket. So if you take 1 minus alpha is common, you will get Q old, and here also Q old. 1 minus alpha is common, plus alpha of this particular equation, it remains. You just need to expand this equation and it will be written in this form. So why I have written this particular equation, that in some textbooks you will see this particular equation and you may get confused. So both are same. It's just a rewritten form of this particular equation. Okay. Next question is deep Q learning, and so this is how the table gets updated. And so it has been seen that there is a common question as to how many such states and actions and the table can accommodate. Okay, so there are examples where there are multiple states and multiple set of actions. So there can be 1,000, 2,000, 5,000, 10,000, 1 million actions, and corresponding to 1 million set of states. So just try to imagine how big the table will be. Here I have shown only 4 states and 4 set of actions. It can be 1 million. So it will be extensively computationally intensive. Computational complexity will increase extensively. Okay, if the number of rows and the number of columns touches million. Okay, so as a result of which, researchers came up with a very new concept, that is deep Q learning. It's not only Q learning or a Q function, it's a deep Q function or a deep Q learning. Try to remember that term. It's a deep Q learning, where they formulated the problem in such a way that the set of states will be, they have used a neural net to implement that, where the input to the neural net denotes the set of states and the output will be a set of actions. Okay, so just try to think of the neural nets which we discussed yesterday, multi-layer perceptron. Okay, where the input states, the input to the multi-layer perceptron are the set of states, and the output of the multi-layer perceptron are the set of actions. Okay, so given a state, what will be the state of action, so that the state change is maximized, the reward is maximized, there is a successful state change. What will be given a particular state, what will be the optimal set of action to be taken, will be governed by the output of the neural net. Okay, so this is the thing. Okay, I'll just show you here the deep Q learning. So this is the deep Q learning basically. Rest of the stories are same. So this is the set of states and the set of actions. So given a particular state, you need to train this particular neural net with the set of states and actions, set of given states and actions. Okay, and given a particular state, what will be the optimal set of action will be governed by this output of this neural net. And the way you train your net is the similar way you train a simple multi-layer perceptron. That means, I mean to say, you need to follow the similar steps of backpropagation. Your optimization problems, backpropagations, graph structure, everything will remain same. The backpropagation algorithm, the stochastic gradient descent as an optimizer, the loss functions, everything remaining same. Okay, you just need to train a neural net, okay, whose inputs will be the set of states and output will be the set of actions. Okay, so this type of deep Q learning approaches are applied where the number of set of states and the number of set of actions are enormously large, which cannot be fitted within a deep in the queue table. Okay, so in those cases, we need to follow these type of things, and the learning procedures are all same, like the gradient descent algorithms and everything. All rest of the things are remaining same. We need to follow those approaches. Okay. Okay, I think this is the brief introduction about the reinforcement learning approaches, and you need to practice. There will be several problems. You will get some predefined libraries, some packages you will be getting. Okay, online you will be getting OpenAI. OpenAI, there is one company, OpenAI, which provides a lot of packages where you can define the agents, the environments. Okay, the set of actions. You just need to install those libraries and packages, and you will get enormous number of examples. Okay, starting from medical domain to do the separately robotic applications, to robotic arms, the video games. Lot of you can just define your agents, define your environments, define your action plans. Okay, and the rest, the job will be done. So my suggestion is that you try to make your hands dirty by practicing more and more with those packages, and try to write new packages, because if the concepts are clear, definitely you can define your own agent, the environment, set of action plans, and you start doing those things. Okay, before jumping into a complex problem. Okay, so those will be my suggestions, and in case you need any kind of help, suggestion, advice, you can contact me offline also. Okay, so you can contact Pankaj sir, and okay, then I'll be trying to answer your queries or mail. So that's it from my side. Any questions? So any questions from the participants?
Hello.
Yeah, hello.
Ha, sir. Is it over?
Yeah. Yes. Yes.
Okay, sir. So any doubts from the participants? I hope everyone has cleared his doubts. Sir, you have given wonderful session. One participant has asked this question, sir. Data required for reinforced learning is same as supervise.
No. That is different. That is different. Okay, that's why I mentioned that example of that OpenAI. Okay, once you start practicing those practically, then you will be able to realize like the type of the nature of the data types, and how you need to model your agents and the environments. Those will be different from the supervised learning approach. Yeah.
Okay, sir. Okay, sir. Thank you very much, sir, for giving a wonderful session on the reinforcing as well as machine learning. So thank you very much. On the behalf of SSBT COET Bambhori, we are very thankful to Dr. Chandrajit Pal, sir. So I hope no doubts from the participants. So we can. Okay, yeah. Thank you very much, sir.
Okay. Thank you, everyone. Thank you, Pankaj sir. Okay.
Yeah. Thank you, sir, for completion of the session within time, sir. Okay, sir.
Yeah. Okay.
Thank you, sir.
Thank you, sir. Thank you.
Yeah. Dear all participants, please stay with us. The valedictory function will be starting very soon at sharp 2 p.m. So please stay with us for a session, as well as those who have given the names for the feedback. They should be ready with their cameras as well as the mic. So we can easily invite you without wasting of the time. So please check your system in case if you have any problem. So we will be with us for testing.